Welcome back for lesson 7.3. You're going to do your first official confidence interval today. Pretty exciting. And before we can do that, we have to discuss a new distribution. And you'll see that this looks very much like the Z-curve, which is the dark black line. This is called the T distribution. And the reason we have to use this new distribution is because when we're estimating a population mean, we don't know the mean, and we usually don't know the standard deviation either, okay? And that's why we skipped part of 7.2. We're going to assume we don't know the standard deviation or the mean. And so that's why we skipped to 7.3. But when we don't have the population standard deviation, and we're trying to use a confidence interval to predict the population mean, we have to use the T distribution. And there's some characteristics about the T distribution that we have to go through. One is we have to use this thing called the degrees of freedom, and that's n minus 1. So your sample size minus 1. We'll have to use that when we are coming up with our critical T values in Desmos. Also, the T distribution is centered and symmetric around 0, just like the normal curve. And the area under the entire curve is 1, just like the normal curve, also related to 100%. The area to the right of 0 is equal to the area to the left of 0, which is also 0.5 or 50%. That's the same as the normal curve. The axis is a horizontal asymptote, the same as the normal curve. It's just a little bit more spread out than the Z distribution. Okay, so let's look at this. So a T, when you have a degrees of freedom 5, which means your sample size would have been 6, is a little bit lower and more spread out here. And then if you increase the sample size to n equals 21 and your degrees of freedom of 20, you're getting a little bit skinnier and much closer to the Z curve. And so the larger the sample size, when you don't know the standard deviation, you're getting closer to the Z curve, but you can't use it. You have to use the T. Okay. So for when we are estimating a population mean for quantitative data, we're going to have to use this T distribution. Okay. So steps for finding the confidence interval. We're going to find the confidence level. Okay. They're going to tell you that in this story. Then we're going to find alpha. Alpha is equal to 1 minus your confidence level. You're then going to take alpha and divide it by 2 because we're cutting our alpha in half. So we're going to have half of our alpha over here and half of our alpha over here. And then our confidence level in the middle. So these three things should add to 100%. Or 1.0. Then we're going to find the critical T value with degrees of freedom of n minus 1. We will note it like this. And I'm going to show you how to find those in Desmos here in a minute. And then you're going to find the margin of error. The margin of error is the give or take that we've kind of been describing with the mean and standard deviation. So it's the give or take in the confidence interval, and it's calculated by taking your critical T, multiplying by your standard deviation divided by the square root of n. And remember, the standard deviation of x bar divided by the square root of n, we learned about this in chapter 6, is our standard error. So the confidence level, the confidence interval, the lower and the upper are found by taking the mean, the sample mean, and adding this margin of error, that gives you your upper, and then taking the sample mean and subtracting this margin of error, and that gives you the lower. Okay, so finding the critical T in Desmos is by taking the inverse CDF of the T distribution with your degrees of freedom, comma, the left area, because remember, Desmos only on the inverse CDF only accepts the left area. So let's look at an example to practice this critical T. It says, what is the critical value of T of 0.05 and 9? So our degrees of freedom is 9 and T of 0.05. Let's go to Desmos so you can see this. So we're using inverse CDF with the T distribution of 9 and 0.05. And that's giving us a negative. So I really needed to do 1 minus that to make sure that I was getting the positive. Now, the T distribution is like the Z where they're symmetric. So when you're just getting these critical T and Z values, most of the time you're just trying to get the number, whether it's positive or negative, doesn't matter. We're just trying to get the number. So this would be 1.833. We usually go to 2 or 3 decimal places. Okay. And then it says, what is the alpha for this critical value? So the alpha is 2 times 0.05. It's 0.1. And that's because a confidence interval is always alpha divided by 2. So if we entered 0.05 into our Desmos, it's because we had cut it in half. So we're going to take 2 times 0.05, and that gives us 0.10. Okay, letter B says, what is the critical value of 98% confidence level in a sample size of 25? So degrees of freedom equals n minus 1, which is 25 minus 1. So our degrees of freedom is 24. So we're looking for T of, and then we have to get our alpha divided by 2. So our confidence level is 98%. So alpha is equal to 1 minus 0.98 or 0.02. And so alpha divided by 2 is 0.01. So we want to find a critical T of 0.01, comma, 24. So of course we're going to go to Desmos. And there it is. The T of degrees of freedom is 24, and our alpha is really, again, should be 1 minus 0.01 for the positive 2.492. And let's go back to the paper. It says, what is the critical value of 85% confidence level and sample size of 20? And so we're going to take 1 minus 0.85, which is 0.15. That's our alpha. And our alpha divided by 2 is 0.15 divided by 2, which is 0.075. And our degrees of freedom, reminding, is n minus 1, which is 20 minus 1, which is 19. So we're looking at T of 0.075, comma, 19. Let's check out Desmos. So I did my calculations here for my alpha divided by 2. And then again, that should be 1 minus. And so our critical T value is 1.500. Okay. So now that we have learned how to find some critical T values in Desmos, we can officially go to our first confidence interval. Now this one, I'm going to walk you through all the pieces and parts and my calculations. So it says, suppose you do a study of acupuncture to determine how effective it is in relieving pain. You measure sensory rates for 15 subjects with the results given. Use the sample data to construct a 95% confidence interval for the mean sensory rate for the population. We are assuming it's normal from which you took the data. The solution is shown step by step by using Desmos calculators. So you can go into the Google Doc if you want and grab this data, copy it, and paste it into Desmos. In my Desmos link, you can see where I did it, but it's good for you to practice because you may have to do this on the final. And so when I did that, this is a 2 find. We find that our N is 15. That's right here. So our degrees of freedom is 14. My confidence level is 95%. So 1 minus that is alpha is 0.05. So my alpha divided by 2 is 0.025. And so I'm looking at a critical value of 0.025, comma 14. So when I do that in Desmos, we get right here. This is my critical value of 2.14. So then I'm going to use that to find my margin of error. My margin of error is my critical t-value there, multiplied by my standard deviation of the data divided by the square root of n. So I'm going to go to Desmos and show you where I worked on this. So I typed in my data. I came up with my mean of my data there of 8.2267. And then my standard deviation of my data is 1.6722. And you can calculate, some of these pieces are probably not in your Desmos link because I copied it before I'm doing this. But we can calculate the margin of error by taking 2.14 and multiplying that by 1.6722 and then dividing by, and then your square root, of course, is down here in your menu. And then there is my margin of error. Now, to find my lower and upper level bounds, I'm going to take my mean, which we found is 8.2267. So I'm going to take 8.2267 and subtract 0.923. Whoops. Subtract 0.923. Oh my goodness. And so my upper bound is 7.3. And then I can also just go over here and just say, or that's my lower bound. And then I'm going to add it. My lower bound was a 7.3 and my upper bound is 9.15. Let me go back to my paper and show you this. So here is my lower boundary and here is my upper boundary. And this is the most important piece, is my description here. It says, we estimate with 95% confidence that the true population mean sensory rate is between 7.30 and 9.15. This is very important. So these are all of your steps to find a confidence interval when you have raw data. Okay. Okay, so let's go ahead and flip the page. And we have another stipulation here. Example 3 says, you do a study on hypnotherapy to determine how effective it is in increasing the number of hours of sleep subjects get each night. You measure hours of sleep for 12 subjects with the following results. I redid this. So if you go to the Google Doc, I think I went through and I got rid of these semicolons. They have to be commas if you're going to copy it into Desmos, just so you're aware. And so we're going to identify the mean. I did all of this in Desmos. You can go and check it out. I copied it there. So the mean we came up with is 8.98, 1.29. My sample size is 12. That means my degrees of freedom is 11. Okay. And X here is number of hours sleep for an individual. And X bar is average number hours sleep for the sample. And that's what we're estimating. Which distribution should we use and why? So we're going to use the T, and that's because the standard deviation is unknown. So it says construct a 95% confidence interval for the mean number of hours slept for the population, assuming normality from which you took the data. And we're going to calculate the error bound or the margin of error. And so to do that, we need to have the T of my alpha divided by 2. Alpha is 1 minus 0.95, so it's 0.05. And alpha divided by 2 is 0.05 divided by 2, which is 0.05. So we need a T of 0.05, comma 11. Now, this is just directions to find the T. This is, you have to find a number with these directions. We're going to do that, okay? And then we're going to multiply that by this standard deviation divided by the square root of n, which is 12. So let's go to Desmos. I copied my data and I did a lot of work in there. For example 3, I found the mean to be the mean and standard deviation to be there. And I can go up here and actually, from example 1, copy this, because then I know how to find my critical T value. And my degrees of freedom is 11, and I want 0.025. So there's my critical T. It's 2.201 if you'd like to use, times 1.29 divided by the square root of 12. That's going to be my margin of error. So let's calculate our margin of error. So 2.201 times 1.29 divided by the square root of 12. Oops, there we go. So there is my margin of error, 0.8196. I'm just going out 4 decimal places. And then to find my upper and lower bound, my lower bound is going to be the mean, which is 8.98. So my lower bound is going to be subtracting my margin of error. So my lower bound is 8.1604, depending on how many decimal places you used on that margin of error. And then I'm going to just show you how I'm going to make another row, and I'm going to copy that. And then I'm going to, and you're going to just show me all this, because you're going to have a project where you're going to have your own data, and you're going to go through all of these steps on your own for your project. So it'll be great practice for the final. So your upper bound is 9.7996. So we are 95% confident, so I'm just going to put 95 there, and then I've got 0.025 out here, 0.025, and I'm just drawing this so I can remind myself. So my critical T value here goes with, this would be the negative critical T over here, and the positive critical T over here, right? And then here's my lower boundary of my confidence interval and my upper boundary. And now we can consider it with our interpretation. So we are 95% confident that the true proportion, no, the true mean, oh, sorry, number of hours of sleep is between between. Now, when I'm describing it here, I'm gonna probably round it to 2 decimal places. So 8.2 or 1 decimal place, 8.2 and 9.8 hours. So be detailed on when you're listing it out. But when you're giving it a description, if you round to 1 decimal place, that's appropriate. Okay. Let's go ahead and look at the next one. I went through another one with me here. So this is the Human Taxone Project. It's working to understand the scope of industrial pollution in the human body. Industrial chemicals may enter the body through pollution or as ingredients in consumer products. That doesn't sound good. In October 2008, the scientists at HTP tested cord blood samples for 20 newborn infants in the U.S. The cord blood of the intrautero newborn group was tested for 430 industrial compounds, pollutants, and other chemicals, including chemicals linked to brain and nervous system toxicity, immune system toxicity, and reproductive toxicity, and fertility problems. There are health concerns about the effects of some chemicals on the brain and nervous system. The table here shows how many of the targeted chemicals were found in each infant's cord blood. Now, I did take this data into Desmos, but you can verify everything here. So we had our sample of 20, that means our degrees of freedom is 19. Because our confidence level is 90, our alpha is 0.10, our alpha divided by 2 is 0.05. So our critical t-value is going to be 1.729 right here. And then I found the margin of error, and we found the lower and the upper, and we have a description. So I do have this data in Desmos under example 4, and the mean came out to be this, and the standard deviation is this. So remember, when you're making a list, if you don't do it in the XY table and you just do a list, if you give it, you have to give it a capital letter, and it has to be using the brackets, but it's a little more efficient than using the XY table to enter data. Okay, so let's go back to our paper momentarily. That's another good example when you have raw data. And then I have another example here. It says a random sample of students were asked to estimate the total number of hours they spend watching television in an average week. The responses are recorded in the table below. In the sample data, use the sample data to answer the following. So we're going to find the mean, standard deviation, the sample size, and degrees of freedom. And I'm going to have you do that. And while you're putting those into Desmos, it says X is number of hours TV, and that would be for an individual, and X bar is number of TV hours for the sample. And so which distribution we're going to use is going to be T, and that's because sigma is unknown. And we can go to Desmos. And you can create you have to call it a capital letter, and then you can put the data in there. That, and then you can find the mean. Oops. And you have to reference that. Make sure mean and standard deviation, they have to be all lowercase, but when you're referencing a list, it's a capital letter. And so the mean is 6.133, the sample mean. And then the standard deviation is 5.51448. And the n is 15. And so that means our degrees of freedom is 14. And so that's right there. Okay. And so our margin of error is going to be the critical T. To go back up and copy that again. And our degrees of freedom, we said, was 14. And our alpha is 0.02. And that means our alpha divided by 2 is 0.01. And so our critical value is 2.62. So our margin of error is 2.62 times 5.514 divided by the square root of degrees of freedom, which is 14. So there is our no, it needs to be 15 RN. Sorry about that. So 3.730. And so our lower boundary is going to be using the mean of 6.133, subtracting 3.73, 6.133, adding 3.73. And you could have run out more decimal places on this, but it wouldn't have changed your margin of error even. Okay, so our margin of error is the 3.73. And then our lower boundary is 2.0403 and 9.863. We are 98% confident. The true population mean number of TV hours per week is between 2.4 and 9.8, actually 9.9, right, if we round appropriately, hours. And this is for statistics students. That's what we said. It was a random sample of statistics students. Okay. Now, we don't always have raw data. So if we don't have raw data, there's an actual computer program, which is awesome in Desmos, that we are going to use for the next few examples. And I want to show you how to use it. If you're in the Google Doc, you can click on the link and it will take you to the computer program. I'm going to show you that in a moment. The link to the computer Desmos program output is, what I used in this lesson is also in Canvas for you to click on. And I would definitely save it as confidence intervals for quantitative data. So in the program, this is just so you'll know what you're entering and you're getting. There's lots of other things that I'm going to show you around. We're going to use this same Desmos link in chapter 8 for a hypothesis test for quantitative data as well. So that's great. So you're going to enter your sample size. You're going to enter the sample mean, and you're going to enter the sample standard deviation. This is only if you're given data. If you're given raw data, then you're going to do it the other way I just showed you. If you're not given raw data and I'm giving you the sample mean and sample standard deviation, you can just put it into this program. You don't need to enter the M0. That's only going to be in chapter 8. You do need to enter the confidence interval, the alpha, I mean. So your alpha is going to be 1 minus your confidence level. So these are the things that you will enter yourself right here. Then there's going to be some drop-down menus at the bottom of this program, and you're going to click on the one for confidence interval, and you're going to scroll down to where it says LB, that's your lower bound of your interval, and UB, that's your upper bound.